All right, strap in, everyone, because today we are taking a deep dive into Einstein's theory of relativity.
Oh yeah, this is gonna be good.
And we're going way beyond the
The classic EMC a 10.
exactly UMCN.
Hmm.
We're going to uncover the really mind-bending stuff, the stuff that makes you question, like, everything you thought you knew about the universe.
It's wild to think about it. I mean, Einstein, when he came up with all this, he wasn't a professor at a fancy university or anything.
Yeah, wasn't he a patent clerk?
Yeah, it's just a patent clerk. Can you imagine revolutionizing physics in your spare time? But the thing is, back then, the world of physics, it was facing a kind of like a crisis, Like
Right.
scientists had this puzzle of the universe, it's almost complete. They thought they had it figured out, but then they found a few pieces that just wouldn't fit. Like Newton's laws, they worked perfectly for centuries, but they couldn't explain some weird stuff about light and motion.
So what were these puzzle pieces that just didn't fit? What was, like, stumping the greatest minds of the time?
Well, one big mystery was this thing called ether, right?
Ether.
Yeah, physicists thought it was this invisible substance that light waves traveled through. But every time they tried to detect this ether, they came up empty.
Oh, so it was like a ghost substance.
Pretty much. And then there was the speed of light itself. You see, equations developed by James Clerk Maxwell, they showed that light always travels at a constant speed. That didn't make any sense according to Newtonian physics.
How so?
Well, think about it. If you're on a train moving, let's say, 50 mile per hour, and you throw a ball forward at 20 mile per hour to someone standing on the ground, that ball looks like it's moving at 70 mile per hour, right? You just add the speeds together.
Yeah, that makes sense.
But light doesn't play by those rules. No matter how fast you're moving, even at crazy high speeds, the speed of light stays the same.
Yeah.
It's mind-boggling.
Okay, yeah, I see the problem. So how did Einstein crack this cosmic code? Did he, like, have a eureka moment while he was, stamping patents?
Well, I doubt it was that simple, but his breakthrough came in 1905. That's when he published his theory of special relativity. And it all boils down to two surprisingly simple ideas.
Okay, I'm listening.
First, the laws of physics, they're the same for everyone moving at a constant speed. Second, the speed of light in a vacuum, it's constant for everyone no matter how the light source is moving.
Those do sound simple.
Right. But they're not. These two seemingly basic principles, they were like a bomb dropped on classical physics.
Ooh, explosive stuff.
Absolutely. They lead to some seriously wild conclusions about space and time. Ideas like time dilation, length contraction, and, get this, the relativity of simultaneity.
Whoa, okay, hold on. Those are some pretty big words. Can you break those down a bit? What do they actually mean, like, for our everyday understanding of the universe?
Let's start with time dilation, all right? This means that time, well, it's not absolute, as we used to think. Time is relative. It depends on how you're moving. Imagine you have two identical clocks, one just chilling on Earth, and the other on a spaceship, rocketing through space at a crazy fraction of the speed of light.
Okay, I'm picturing it. What happens to the clocks?
Well, special relativity tells us that the clock on the spaceship, it'll actually tick slower from the perspective of the observer on Earth.
Wait, really? Time actually slows down on the spaceship?
Yeah, it's wild, right?
Like-
It goes against everything we think we know about time. But that's exactly what Einstein's theory predicts, and experiments have shown it to be true again and again.
Whoa, okay. So time isn't this, like, fixed thing. It's flexible, it bends, it stretches. What other crazy implications did Einstein discover?
Well, time dilation is just one piece of the puzzle. Special relativity also predicts something called length contraction, and this means basically objects moving at really high speeds, they appear shorter to someone who's standing still.
Hold on, wait. Are you saying things actually shrink when they move fast? Like, is it an illusion?
Kind of. It's not an illusion exactly, but it's a real effect of the speed of light being constant. Think of it like this. To make the speed of light always the same, our measurements of space and time, they kind of have to adjust, right?
Huh, I guess.
Uh,
And that leads to these weird, like, distortions.
Exactly. So that spaceship, remember, if we saw it zooming by close to the speed of light, it would look squashed, like compressed in the direction it's moving.
No way.
Yeah, and get this, the faster it goes, the more squished it gets. It's like someone sat on a balloon animal.
That's so weird.
Yeah, but here's the thing. This length contraction, you only see it from the point of view of someone who's not moving with the object. So someone on board the spaceship, everything would look normal to them.
Man, this is, like, really messing with my head. It's like the universe is playing tricks on us, messing with our perception depending on how fast we're going.
It's more like, the universe has these rules, right? And we're just figuring out what they are. And speaking of rules, there's one more crazy consequence of special relativity. It's called the relativity of simultaneity.
Relativity of simultaneity. Okay, hit me with it. I'm ready for another brain twister.
It means that basically whether two events happen at the same time, it depends on where you're standing, your frame of reference. So two things that look simultaneous to one person might not be simultaneous to someone else who's moving relative to the first person.
Wait. So, like, what might seem like a single moment in time for one person, it could be spread out over time for someone else.
Exactly. It really messes with our sense of a universal now. It's like there's no single universal clock for the entire universe.
Mind blown. But as crazy as all this sounds, I mean, this stuff has been proven, right?
Oh, yeah, definitely. All these predictions of special relativity, as wild as they seem, they've been tested and confirmed over and over again in experiments.
That's incredible. So Einstein's ideas, they weren't just some, like, thought experiment, right? They actually describe how the universe works on, like, a fundamental level. It makes you wonder how other scientists reacted to all of this. I mean, did everyone just accept it immediately, or did Einstein, like, have to fight to convince people?
Yeah, it wasn't an overnight thing like, oh, Einstein's right, case closed. It took some time for these, pretty radical concepts to catch on.
Right, I bet.
It's a big deal to challenge, like, centuries of accepted scientific knowledge. Not everyone was ready to jump on the Einstein bandwagon right away.
So what were some of the biggest roadblocks Einstein had to overcome? Like, why were some people so resistant?
Some scientists, they were just skeptical, which is natural, when someone comes along and shakes things up. And some folks, they probably just had a hard time wrapping their heads around the math. It can get pretty intense. But ultimately, the thing that really solidified special relativity, it was the experimental evidence. Like, as technology got better, scientists could test Einstein's predictions, and the results, they kept proving him right.
Oh, wow. So they actually saw these effects happening in the real world.
Yep. Real world observations proving that these ideas, these crazy out there ideas, they were actually spot on. That really changed the game. And it laid the groundwork for Einstein's next big breakthrough, which was his theory of general relativity. This one, it brings gravity into the mix.
So again, now we're really stepping things up. General relativity. What's the elevator pitch for that one?
So you remember how special relativity was all about the relationship between space and time?
Yeah.
Well, general relativity, it's about how this space-time fabric, the very fabric of the universe, it gets warped and curved by mass and energy.
Space-time fabric. Sounds like we're getting pretty cosmic here.
That's actually a good way to think about it. Imagine, like, a trampoline, right? If you put a bowling ball on it, what happens?
It makes it dip, sinks down in the middle.
Exactly. Now, imagine rolling a marble across the trampoline. What does it do?
It would curve inward, go towards the bowling ball like it was being pulled in.
Exactly. And that, my friend, is basically how Einstein described gravity. It's not some mysterious force acting at a distance. It's the curvature of space-time caused by massive objects.
So Earth isn't being pulled toward the sun by some invisible force. It's just following the curves in space-time made by the sun's mass.
You got it. It's a whole new way of thinking about gravity. And just like special relativity, general relativity has been backed up by tons of evidence, from the way starlight bends around the sun to the very existence of black holes.
Black holes, now we're talking. Those things are seriously mind-blowing.
They are, and they're one of the most incredible predictions of general relativity. Black holes are regions of space-time where gravity is so strong, so intense that nothing, not even light, can escape.
Whoa, that's insane. So if light can't even escape a black hole, how do we know they're even there?
That's the thing, you can't see them directly, but we can detect their presence by the way they affect stuff around them. Like, if a black hole is pulling in gas and dust, that material, it heats up and emits X-rays, and we can detect those with our telescopes.
That's crazy. It's like these cosmic monsters are out there lurking in the dark.
Right. It's wild. But it's also a testament to the power of Einstein's ideas. He took us from a universe where space and time were absolute, unchanging, and showed us that they're actually interwoven, relative, and they can be warped and curved.
It's like he took our rigid view of the universe and, like, made it flexible, dynamic.
Exactly. His ideas opened up so many new possibilities, new ways of thinking about the universe, and we're still learning and discovering new things because of him.
That's pretty amazing. You know, it's mind-blowing to think that one person's ideas could have such a massive impact on how we understand the universe. like Einstein did.
It really is incredible.
We've gone pretty deep into these mind-bending ideas of special and general relativity, but I'm curious, how did Einstein's theories affect things in, like, the real world, beyond the theoretical stuff?
That's a great question. I mean, it's easy to get caught up in the elegant math and the beauty of it all. But Einstein's work actually had a huge impact on technology and our everyday lives. Like take GPS, for example.
Right, GPS uses both special and general relativity to, like, give us accurate location data.
Yeah, remember how we talked about those atomic clocks on GPS satellites?
Uh-huh.
They have to account for time dilation because of, their speed and the weaker gravity they're experiencing up in orbit.
Yeah, that was wild.
It is wild. If we didn't make those relativistic corrections, GPS would be totally useless. We'd be getting lost all the time.
Oh, I would definitely get lost, no doubt.
Right. It's amazing, right? This theory that seems so abstract, it's actually woven into something we use every day, like to find our way to the grocery store.
Yeah, totally. It's like these theories that seem so out there, they're actually a part of our daily lives.
They really are. And another big example, nuclear energy.
Oh yeah, E-beam co, the most famous equation ever.
Right. But it's more than just a cool equation. It actually explains the relationship between mass and energy. It shows that, like, even a tiny bit of mass can be converted into a huge amount of energy.
I remember seeing that equation on, like, T-shirts and posters everywhere. But seriously, what does E-B co actually mean for, like, the real world?
Well, that equation, it's the basis for how we understand nuclear reactions, both fission, splitting atoms, and fusion, combining them. Nuclear fission is what powers nuclear power plants.
Okay, that makes sense. But wasn't Einstein, like, really concerned about nuclear weapons? I thought he was a pacifist.
He was, very much so. And it's kind of ironic, but his work, it actually led to the development of both nuclear energy and nuclear bombs. It's a powerful reminder that scientific discoveries, they can be used for good or bad. It depends on us.
That's true, yeah. We have to make those choices. But aside from nuclear stuff, did Einstein's work lead to other cool technology?
Tons. Think about photoelectric cells used in solar panels, lasers, even medical imaging techniques. It's pretty remarkable.
Wow, so his impact really is all over the place. It's not just, like, changing our understanding of the universe, but actually changing how we live in it. Amazing.
It's pretty profound when you think about it. But going back to that point about understanding the universe, I mean, Einstein's work really did revolutionize how we think about space, time, gravity, like our whole conception of reality.
Yeah, I mean, before Einstein, people thought space and time were these absolute unchanging things.
Right. But relativity showed us that space and time are, well, they're relative, they're connected, and they can be warped, curved by mass and energy.
It's like he took our rigid view of the universe, all straight lines and fixed points, and then said, no, it's actually flexible, dynamic, and way more interesting.
Exactly. And it opened up whole new areas of research, like in cosmology, astrophysics, particle physics, and it even led to predictions of things we couldn't even imagine before, like gravitational waves.
Gravitational waves, those are like ripples in space-time, right?
Exactly. And they were only recently detected, like 100 years after Einstein predicted them.
Wow. So we're still making discoveries based on his work even now.
Yeah. And, beyond the science itself, Einstein's story, I think, is also just really inspiring. It shows the power of curiosity, imagination, and, the courage to question everything. He was a true visionary.
It's incredible to think that, like, one person with a pencil and paper just thinking could unlock these secrets of the universe. Pretty amazing.
It is. And I think it reminds us that there's always more to discover, more to learn, and the universe, it's way more wondrous and strange than we could ever imagine.
That's a perfect note to end on. Thanks for joining us on this incredible journey through Einstein's universe. And to all our listeners out there, keep those minds curious and those imaginations fired up. There's a whole universe waiting to be explored.